good evening to all the European participants. Good afternoon or good morning to the US guys. I would like to welcome you to our webinar today with the title Why and How to Replace the Ingress Test by Deterministic CCIT Methods. The webinar will take like 45 minutes of presentation. During that, you will have the chance to write down questions, and we will have 15 minutes Q&A session in the end and try to answer all your questions. As I'm a German guy, just one preliminary note, please do not spoil any scores of the German soccer game into the chat. I would really appreciate that. So just as introduction for your presenters today, I'm the moderator. I will guide you a bit through the webinar. And Philippe is our presenter today. He's our Business Development Europe CCIT Solutions guy with more than 25 years experience in leak detection and leak testing, and now focusing on really CCIT solutions and everything that we do about that. Philippe, I will give you the lead, and have fun to everybody.
Thank you, Lucas, for this introduction. Hello, everybody. Welcome for this webinar. Let's start with first the agenda of this webinar. Very quickly, we will remind theoretical basics before to present the scope of our comparative study. Today, we will present for the first time the result of this comparative study between blue dye and deterministic method. Then more technical result, I would say. And as a conclusion, we will try to answer to the question which alternative to the blue dye test. So theoretical basis, just to remind something about rules and the regulation, to define what is a leak, what is a defect, in order to have a good understanding of what we will explain later on. So, of course, container closure integrity is something important for pharma industry. As you know, it's an essential part of suitability, especially in the aspect of protection against three main contaminants. Moisture, some products, some drugs like inhalation drugs, very thin and dry powder are very sensitive to moisture. Another contaminant could be oxygen, which can affect the efficiency of the drugs. And for sterile product, of course, the biological contamination is the main issue. So regulation on industry best practice are changing slowly, but they are changing. And now USP 1207, for example, is encouraging a move toward deterministic method instead of probabilistic method. We will explain that. And in the new revision of the Annex 1, for example, a statistically valid sampling plan should be utilized, which means to increase the number of samples for IPC tests, for example. So a better validation means more data, more tests. And for sure, if your test is descriptive, that could be a big pain for you. So in practice, this new Annex 1 means that if you are testing today few tens samples per day, you should go for a larger sampling rate and test in the near future a few hundred samples per day. Just to remind that, of course, container closure should be closed by appropriately validated method. Just to remind that there is no magic CCIT method, and in order to select the right one for your application, as you know, we need to consider both the container and the drug inside the container. The complete system needs to be addressed for the CCIT application. Just a reminder that container closed by fusion should be subject to 100% integrity test, of course, if it is possible, if there is a technology which is able to address 100% inline test. And yeah, statistically valid sampling plan should be utilized. Again, that means more data, more tests. Just to remind or to clarify, deterministic method, deterministic can be defined versus probabilistic. Something which is deterministic is predictable by a chain of events. You know you can predict what will happen because everything is under control. And this is performed by measuring either physical or chemical endpoint. And as a result, we get objective and quantitative results, which is just the opposite of so-called probabilistic method, as the blue dye or the microbiome Ingress test are. Okay, it's time to engage you for the first poll of this webinar. So I give the hand to Lucas for that.
I was muted. We'd just like to want to know which type of technology you are currently using. If it's only the dye ingress method, if you make a mix of that, if you only use deterministic, or maybe neither of them. Okay, we will wait a few more seconds until everyone has voted who wants to. Okay. So, Philippe, here are the results. It's quite interesting and very good to see that no one is using the dye ingress test and do not want to change. Otherwise, we would try to convince you for sure.
Okay. So let's continue this presentation. I just want here to mention what should be or what are the ideal attributes for a CCIT method. Of course, the ideal method should be deterministic, non-destructive, objective, which means not operator dependent, traceable, if possible with software, CFR 21 Part 11 compliant, sensitive, or at least with a higher sensitivity compared to the existing blue dye, easy to set up, easy to use, high-speed test because time is money, and easy to automate. And not less important things, versatile, because you have a lot of different combination of packaging and drugs to test, from vials to IV bag, bottles, plastic bottle, glass bottle, blisters, syringes, cartridge. So it's important that the method you will select can address a large range of application. Let's see how is the blue dye regarding this attribute. So of course, first point, the blue dye by nature is stochastic as a biocontamination, so it's not deterministic, it's probabilistic. In some case, not all the case, but it's a destructive method because for a non-transparent container, you have to open the container in order to see if you have blue inside. In most of the case, the visual inspection is performed by an operator, which means that the decision is taken by the operator, so it's not 100% objective. If the operator is doing the test, he will record manually the results, so it's not fully traceable. We will show that in our study. It is not very sensitive compared to the other technology which are available now for tests. It's quite easy to set up, even if the cleaning stage it's sometimes not very easy to perform. It's a medium speed test and quite difficult to automate because of all this step of immersion, cleaning, and so on. So today, and this will be the conclusion of this webinar, we will try to compare this blue dye with the three technology proposed by Pfeiffer Vacuum, which are OES, optical emission spectroscopy, mass extraction, and helium mass spectrometry. So in order to argue, we have performed a comparative study on a wide range of samples, more than 500 samples, between the blue dye and these three technology. So first, just to clarify or to remind what is a leak. A leak is a defect in the wall of an object, of a container, and that's allow gas or liquid exchange from one side to the other. So for us, if there is a liquid or gas exchange, there is a leak. Of course, if you have a defect, and if this defect is blocked, there is no leak, but there is still a defect. For theoretical calculations, the geometry of the real defect can be approximated by either sharp edge orifice or pinhole, or a channel, or microchannel, or capillary. As a result of a leak, we can measure, and this is the purpose of our equipment, we can measure the leak rate. And the leak rate describes the amount of gas that penetrates through a defect in a certain time at a certain pressure. In Europe, the most common leak rate unit used is millibar liter per second or atmosphere cubic centimeter per second, which are almost equivalent. That means that if you have a leak rate of 1 atmosphere cubic centimeter per second, you will collect, as you can see on the picture below here, you will collect 1 cubic centimeter of gas in 1 second at atmospheric pressure. Okay. Of course, the real world defect is not a perfect whole. Usually we have a complex and various shapes, lengths, form, and so on. And even more, it can change over time. So for theoretical calculation, we can estimate the size of a perfect hole, what we call an effective diameter, of the equivalent hole corresponding to the surface, to the area of the real defects. We talked already about orifices and channels. Both geometry are not equal. For a defined diameter, orifice and channel will not give the same leak rate. So they will not have the same impact on the integrity of your container. Sharp edge orifice is only defined by a diameter because the length of the leak path is very small. We have like a diaphragm, and sharp edge orifice is defined just by a diameter. And if you are using a micropipette, glass micropipette is very close to a pure sharp edge orifice. If now you consider a microchannel, you have to consider not only the diameter of the defect, but also the length of the leak path. And of course, this will affect the leak rate or the flow going through these defects. Laser drill hole in glass vials or syringes are equivalent to orifices if the diameter of the hole is larger than 3 microns. On the other side, submicron real defects are equivalent to microchannel. Okay, you are probably using a positive control leak artifact to generate positive control. So here you have the list of the well-known leak artifact which can be used: the glass micropipette, which is a pure sharp edge orifice; the laser drill hole, which is close to an orifice because the diameter cannot be below 3 micron, something like that; the microtubes, and the copper wire or calibrated wires you can put between the neck of a vials, for example, and the cap, or between the plunger in the syringe and the barrel. But in fact, the best way to select positive control is to select this positive control directly from the production. So just to remind that if you want to generate positive control using leak artifact, the selection of this leak artifact must be as close as possible with the real defect generated in production. So for example, if you consider a blister pack, the risk is to have a leak in the sealing area, and you can easily understand that the sealing area is few millimeter length, and that we are close to a microchannel or capillary. Okay, time to engage you for this second poll with Lucas.
Yeah, the next question would be, what kind of defects are you using to validate your CCIT methods? So you just heard some of them. And what would be interesting if you select none of the above? Maybe you can just quickly write down in the chat what else you use for defect creation for positive controls. Okay, we'll wait just a few more seconds. Okay. So Philippe, here are the results.
Yeah,
A quite good mix, I would say.
yeah,
And a lot of
yeah,
people who use real defects from production. What is
always. Yeah, quite surprising. It's a quite high level of people using real defect from production compared to our experience with our customer here. Okay, if you are okay, I can continue the presentation with the second part, which is Pfeiffer vacuum comparative study, what we have done. So again, comparison of the blue dye with three deterministic method. And before to start to explain how we perform the test, just a few words about the state of the art with the blue dye. So we decided to make this study starting from two references. The first one is a study performed by Burrell and Hall, performing a correlation between the dye ingress method and the microbial ingress test using microtube to make this study. And the other study is the study performed by Kirsch and Hall, which is at the origin of the mole concept in the USP. Kirsch and Hall made the correlation between microbial ingress and helium leak. So, I'm using glass micropipette. You have the information here. So again, this study is really at the origin of the mole concept, mole maximum allowable leak limit defined in the USP 1207. That corresponds to a helium leakage of 6 × 10⁻⁶ millibar liter per second, for which the probability of microbial ingress was below 10%. You can see on this graph the microbial ingress failure rate versus the helium leak rate, or at the top, the mean diameter of the micropipette. So Kirsch demonstrates that with this condition of contamination, the limit for the microbial contamination is a sharp edge orifice of 0.2 micron, 0.2, 0.3 micron. So this is the reason why we decided to make this study using glass micropipette. And the other reason why we decide to use microtube is to be similar to the study performed by Burrell. So Burrell makes a study again between dye ingress and microbial ingress, and these two methods are both stochastic, so they have the same behavior. And you see Burrell use more or less the standard ISO condition, and microtube 3 centimeters long to perform this study. And the result is that the blue dye test with this condition, this defect is around 15 microns. So this is the reason why we have decided to prepare samples, first with glass micropipette, 7 diameter, between 0.1 and 10 microns, 30 samples for each diameter, and 30 negative control, just putting glue on the hole on the vials. Then we did the same for microtube, for capillary, 3 centimeters long, again 7 diameter, between 2 micron and 40 micron, 30 samples for each diameter, and 30 negative control as a reference for our background. So we use a 20 ml vials for that, and here is a sample preparation. As you can see, the leak artifact, so the micropipette or the microtube is glue, is located on the side of the vials, and glue with a UV glue. We have decided to fill the vial with 6 ml of WFI water, and to leave gas headspace around the defect. We did not immerse the defect inside the liquid. So we take care to have no contact between the defect and the liquid during this study. And as a gas headspace, of course, because we want to perform measurement with helium, with OES and mass extraction, we have to put helium inside. So we decide to work with a gas mixture, 20% helium, 80% nitrogen, because 80% nitrogen is close to the natural concentration of nitrogen in air. So that's allowed to make the detection of helium using the 20% helium. to make the detection with OES tracking the 80% nitrogen, and mass extraction is measuring the global flow escaping from the sample. So we don't care what is the gas we want to detect, we measure everything. And as I mentioned, the leak artifacts are located in the gas headspace, no contact with the liquid, because as I will show you, this has an impact on the sensitivity of your blue dye. So we make the test in this sequence: first helium mass spec, then optical emission spectroscopy, then mass extraction, and finally blue dye, because it's a destructive test, so we cannot retest. So we did the blue dye at the end. So in total, we prepare more than 500 samples. So first we drill a hole in the vials, then we install the leak artifact, we glue it with a UV glue, we fill the vials with a 6 ml of WFI water, and then using our equipment, we generate the gas headspace. We first evacuate the air from the bottles, and we flush the bottle with the gas mixture, 20% helium, 80% nitrogen, before to remove the tooling here and put the rubber plug on the vials. And finally, we crimp and we put a label on each vials. So the three technology, in few words, that we use for this test is first the helium mass spec, which is more or less the golden reference for CCIT. It's the most sensitive method for leak testing or CCIT, because it's very selective, as you can see on this picture. With a mass spectrometer, you only measure the helium molecule without any interference with the other gas. So this is the reason why it is so sensitive. The pain is that we need helium inside the container, and it's not easy to do depending on your container. Then we use also the mass extraction technology, which is based on a microflow sensor. Here you have a cut view of the sensor, as here you see that the measurement is a direct measurement of the leakage. The container to test is located in a vacuum chamber, in a test chamber here, which is connected to a vacuum tank, and we measure the direct leakage through the sensor using this technology, so-called mass extraction. And at the end, we have the optical emission spectroscopy, which is a multi-gas sensor, multi-gas analyzer, able to detect not every gas, but at least nitrogen, carbon dioxide, argon, moisture, alcohol. But for example, we cannot detect oxygen or helium with this technology. And the principle is to generate a plasma. That means with an electron beam, we excited the gas, and the de-excitation of the gas will give us light corresponding to the different molecules escaping from the container. So for all this technology, what we are doing, we are performing a global vacuum test on your container, which means that your product will be installed, located in a vacuum chamber. We will decrease the pressure around your product. With these three technology, the differential pressure, assuming you have atmospheric pressure inside your vials, is 1 bar. You have 1 bar differential pressure, and we are measuring the gas escaping from the container. So with helium, we need helium inside, and we will measure the helium flow escaping from the container. With mass extraction, we will measure the global flow escaping from the container. And with OES, depending on the gas you have inside, if you have air or nitrogen, for sure, we will track nitrogen. But if you have, for example, argon or carbon dioxide, we can also decide to track other gas like argon or carbon dioxide. So mass extraction and optical emission spectroscopy, it's easy to understand, do not require any sample preparation, do not require any tracer gas. But of course, at the end, as you will see in this study, it's less sensitive compared to helium. So corresponding to these three technology, we have a product portfolio of 3 equipment. the ME2 equipment for the mass extraction, the ISM 2000 for the helium mass spec, and the IMI 1000 for the OES. All these equipments, of course, propose a deterministic method, non-destructive. It's an integral vacuum test. What we will provide as a result is a quantitative measurement of the leak rate in millibar liter per second. And all these equipment are equipped with CFR 21 Part 11 software. Okay, few words about the die Ingress, just to understand how it works, or to remind how it works, and what are the limits of this technology. First step is for sure to immerse the product inside the blue bath and to decrease the pressure above the liquid. And if you have big leak, you can even see some bubbles escaping from the leaky container. But you do that during 30 minutes, 1 hour, or sometimes few minutes, depending on your recipe. Then the second step is a die ingress sequence. So you recover atmospheric pressure above your liquids, and you leave your product inside the blue bath during 30 minutes, a few minutes, or 1 hour. And if you want to increase or improve the sensitivity of the blue die, sometimes you can play with overpressure in order to push the blue die inside the defect and get a higher sensitivity. And finally, third step is the inspection, which is performed by an operator. In most of the case, it's a visual inspection, but sometimes this can be performed by a spectrophotometer. Okay, here you have the homemade Pfeiffer vacuum blue dye equipment. Just to mention that we use the same dye solution, 1% with 0.25% sodium dodecine sulfate in deionized water, as same condition as the barrel study. We make a small change compared to the barrel condition. We just increase the immersion time because we are dealing with a larger volume of liquids, so we have a larger dilution effect. And to compensate this dilution effect, we decided to increase a little bit the immersion time at vacuum. Here you have more or less the standard conditions, the standard ISO condition proposed for the blue dye test. And you have here the condition we used, minus 37 kPa, which correspond to the modified ISO. 60 minutes for the immersion time at vacuum. This is the reason why, well, I explained the reason why we increase this immersion time, and 30 minutes at atmospheric pressure before to perform the visual inspection. It's a very interesting method, but blue dye depend on many factors, and then at the end it's complex to estimate what will be the sensitivity of the blue dye recipe depending on your product, because blue dye sensitivity will depend on the container, of the defect geometry, we talk about that, of the inspection, of course if you have an operator, of the dye ingress recipe, of the air ingress condition, of the drug itself. So at the end, all these factors will have an impact on the sensitivity of your blue dye, and it's easy to understand why this is a probabilistic method, because you cannot predict what will happen. There is so many parameters, you cannot control everything. So because of that, I would say the question is, do you know the sensitivity of your blue dye test? Did you measure the sensitivity? Do you have an idea of the sensitivity of your blue dye test? And this is a key point if you want to move from blue dye to deterministic method, because on a deterministic method, you will have to fix a set point. And if you don't know the set point, this could be an issue. Again, time to engage you for a third poll with Lucas.
Yeah, I just opened it. So you've heard about the parameters and especially immersion time. And in our experience, most of the time, it's less than 5 minutes immersion time. But we would like to understand how long your blue dye test is, especially when we compare that to the more or less the standards that are available, like the ISO, for example.
Yeah.
Okay, we just wait a few more seconds. Okay. So the results you can see here. So it's interesting, most of you have at least took a longer time, between 10 and 30 minutes.
Yeah. Okay, interesting.
Okay.
Thank you
Okay.
for this
Move
feedback.
forward, Philippe. Thank you.
Yeah. So here is the result of this study. And just to illustrate the impact of the defect geometry, you see here the detection limit of our blue dye recipe here, as I already explained, on vials with micropipettes. So you see that our detection limit is around 5 microns micropipettes, and we can compare that to the microtubes, and you see the 3 centimeter long microtubes give, of course, a different result, and the detection limit for the microtubes is around 20 micron, which are very similar to the result proposed by Burrell. So hopefully the physics laws are the same for blue dye and our deterministic method, and you see that the defect geometry has a big impact on the sensitivity of your blue dye test. Another point which is interesting is which sensitivity if air and water behind the defect, or air or water behind the defect. So we make some tests and we decide to work with air behind the defect because that gives to the blue dye recipe a higher sensitivity compared to water behind the defect. And this is probably due to the viscosity of air, which is much smaller compared to the water viscosity. We didn't make a long study about that, but you see this is another parameter that sometimes is difficult to control and which can affect the sensitivity of your blue dye. Let's go for the results of the study, and I will show you a different curve corresponding to the different measurement for the different technologies. So let's take a few seconds in order to explain the graph you will see on the next slide. Okay, you see on this graph the gas leakage in millibar liter per second versus the defect diameter. And the red dot here correspond to the 30 leaky samples for one given diameter. For example, 20 micron, you have this 30 measurement here. And the red line below correspond to the average value of this 30 measurement of leaky samples minus 3 sigma. And we have the same for the lower part of the graph, which correspond to this dark cross with a dark line here. The dark cross correspond to the 5 negative control, and the dark line to the average value plus 3 sigma. So of course, if you have a difference, a big difference, or no overlap between the average value of the leaky sample minus 3 sigma and the average value of the tight sample plus 3 sigma, the method is applicable and you can use it. Of course, if it is reverse, then you have everything in the same area and the method cannot be used anymore. You reach the limit of sensitivity of the method. So let's have a look. All the graphs are very similar. So just to show that with 20% helium, we can easily detect down to 5 micron or even a little bit below capillaries. Of course, the 2 micron cannot be detected. So much more sensitive compared to the 20 micron detection limit of the blue dye. We did the same with optical emission spectroscopy. And with optical emission spectroscopy, we can detect down to 7, 8 micron capillaries. Again, more sensitive comparing to the blue dye. And we did the same with mass extraction. And the detection limit is below 15 micron. We can estimate between 12 and 15 microns. Okay, as a summary of the measurement performed on capillaries, on micro tubes of 3 centimeter long, here you have the detection limit of the 3 technology compared to the blue dye. I just mentioned here the cycle time we use to perform the test, so 25 seconds for helium, 25 seconds for optical emission spectroscopy, and 75 seconds for mass extraction, which is similar to the blue dye test duration for one sample if you operate on a batch of 100 samples, roughly. And we did the same for micropipettes, but of course, as we have demonstrated before, a glass micropipette of 20 microns give a larger flow compared to a microtube of 20 microns. So it's not a big surprise to see that with 20% helium inside the container, we can detect that down to 0.1 micron glass micropipettes. And yeah, and we have the same for optical emission spectroscopy. We can detect down to 0.6 or 0.7 micron glass micropipettes. And the same for mass extraction. We can detect between 1 and 2 micron glass micropipettes. So again, a summary of this measurement. You see that these three methods are more sensitive than blue dye. It's not a surprise, but just to indicate the detection limit of each method. Okay, conclusion. Which alternative to the blue dye? So I want to use the first table. I start with this table. I would like now to complete this table with the result of this study. And if we try to make the analysis of helium method, we can see that it's of course a deterministic method. In most of the case, because you need to put helium inside your container and it's not so easy, sometimes it's a destructive operation. So it's considered, let's say, helium is considered for pharma industry as a destructive method. It's objective, traceable, no problem. It's very sensitive. Again, this is the most sensitive technology for leak testing. It's not so easy to set up because you have to charge your product, your container with helium. The test itself is very fast, very easy, but what is difficult is to put the helium inside your container and to know the helium concentration you have in your container. It's quite fast and it's difficult to automate because of the charging sequence. For mass extraction, it's deterministic, no doubt, non-destructive, no doubt, objective, same, traceable, same. We have a software, we track everything. The sensitivity is, of course, better than the blue dye, but not so sensitive compared to the helium test. In fact, it is very easy to set up and easy to use, no sample preparation again. The speed is not so high compared to let's say to the blue dye, and it can be automated quite easily. And finally, we have the OES, the optical emission spectroscopy. It's very deterministic, especially when you have air inside your product. You are sure that you have a well-known and stable concentration of nitrogen inside your container, so that gives you a fixed reference with no variation, so very accurate measurements. It's non-destructive, objective, traceable, sensitive. Not so sensitive compared to helium, a little bit more sensitive compared to mass extraction. The three are much more sensitive compared to blue dye. Again, easy to set up and to use, no sample preparation. High speed, similar to what we can achieve with helium, and quite easy to automate. Just to mention here, with this technology, we are not depending on the free volume around the product. The sensitivity is not affected by the free volume, which means that we can imagine to test several parts at the same time, to test a batch of product with the same sensitivity in order to increase the throughput. And all these technology are quite versatile and can be used for many applications. As you can see on this picture, from blister pack, IV bag, glass vials, plastic bottles, cartridge, glass syringes, test per batch here. So very versatile, which means that all these technology are applicable for a wide variety of packaging. I just want to mention that you have different phases when you need leak testing in pharma industry. The first one is when you developed a new packaging, when you want to qualify a new packaging. And for this phase, of course, you need to get high sensitivity measurement because you want to compare different design, you want to compare different material. So you need sensitivity, and the helium is really the method which is the best one for this stage. And when you want to test in production or during commercial safe life for stability assessment, OES and mass extraction can be used for the two other steps. Okay, the two main benefits, it's quite easy to understand. It's to use a deterministic method is to improve the quality and to save money because it's a non-destructive technology. And with this deterministic method, we can imagine to delay the operator, because if you have a deterministic method, the operator is just here for loading and loading the part. He has no added value. So we could easily imagine to replace the operator by a pick and place robot, for example, and of course to save costs due to the labor cost of the operator. Moving from a die ingress to a deterministic CCIT method, first step, and it's quite important, is assessing the sensitivity of your die ingress test, which is a prerequisite to upgrade to a deterministic method. And Pfeiffer Vacuum can support you for that. You, as a pharma customer, can send us samples. We can create defects using microtube. It's quite easy to manipulate microtube on these samples. We can make a different diameter, different geometry. We can measure these leaky samples, positive control with OES, for example, the deterministic method. Send back the product to you, and you will perform the die ingress test. And then you will have a direct correlation between what you measure with your blue dye test in respect with what we measure with our technology, which is a leak rate in millibar liter per second. And this, for me, this is really the first step if you want to move from a die ingress to a deterministic method. Okay, it's time to engage you for the last poll of this webinar with Lucas.
So our last question would be, what is your main motivation to change from die ingress test to a deterministic test method? We just put a few factors here, which might be interesting. Okay. We'll just wait a few more seconds. Okay, so we'll share the results. Quite interesting. A lot of people want to improve their sensitivity.
Yeah.
I think all the deterministic methods presented here can help with that. Follow the latest guidelines.
Yeah. And get highest throughput. Yeah.
Okay, word to you again, Philippe.
Yeah, thank you for this feedback. To conclude this presentation, this webinar, I want to just to summarize on one slide the different vacuum CCIT solution. So let's consider again the Kirsch study with this curve, the microbial ingress failure rate versus the orifice diameter. With this mole level at 0.2, 0.3 microns. And we can here try to illustrate the different detection range of the die ingress, of the vacuum decay test, of the mass extraction, of the OES, and finally of the helium. Using low concentration helium, you can imagine to detect large leak, above 10 micron, it's already a large leak, or very fine leak, down to 0.1 micron and below. Regarding the cycle time, again, we already mentioned that you can compare the cycle time of the different technology we use in our study, and this is an estimation of the cycle time of blue dye, considering a batch of 100 or 50. We can have a test duration of 75 seconds, which means comparable to the mass extraction, and 2 minutes. Okay, just before to start the Q&A session and to conclude this webinar, I would like to welcome you on our virtual booth. You will find online on our website this virtual booth with a lot of information, not only considering our product, but also a lot of information considering CCIT, trade show, the service we can propose. So do not hesitate to visit our virtual booth. And I would like to welcome you on our next exhibition, next trade show in US for the NDNAM West show in Anaheim. And this will happen in August. And in October, it will be a pleasure to welcome you in Paris for the PharmaPack Europe. And yeah, now I'll let you open for the Q&A session with Lucas.
Thank you, Philippe, for this great presentation. We do not have so many questions yet, so
okay.
I just want to encourage you again. Now it's the time to ask if you have something. But just to cover the time, I will take some of the interesting questions from this morning, Philippe. Like one question which was interesting, I think, was how about containers filled with ethanolic or proteinous solutions? How do we assess that?
Ethanolic or
protein-filled solutions?
Yeah, okay. So with our technology, it's quite easy to detect liquids, if it is a water-based liquids or alcohol. Depending of the oil, oily liquids is quite difficult to detect, even at low pressure. And considering high protein drugs, the risk with high protein drugs is to have a glocking effect of the very small defects. And of course, as I explained when I explained the leak, if a defect is glocked, we will not measure any gas escaping from the container, and we cannot detect the leak. So indeed, this is a limitation factor of all this vacuum technology. If the defect is glocked by whatever the reason is glocked, we will not measure anything. This is true for also for vacuum decay. This is true for blue dye as well. Yeah.
Maybe one more question. Does Pfeiffer Vacuum supports in regards to documentation and qualification of an instrument or process?
Yeah, what we propose together with our equipment is a complete package, including IQ and OQ documentation with a factory acceptance test and site acceptance test, of course, on customer side. Of course, Pfeiffer will support you during the PQ to give a full support in order to answer to your question and to help you during the process qualification you will perform if you decide to use our technology.
One more question. Do you think helium leak testing could be also used in production as IPC, or do you not recommend that?
Yes, it's possible. It's not easy. I know few examples of helium tests used as IPC test, but two things to consider. Yes, it's possible, but why to use a very sensitive method except if you need high sensitivity measurement? So in IPC test, in most of the time, we do not challenge the sensitivity below, I would say, 10 to minus 4, 10 to minus 5 in the best case. So yes, we could imagine to use helium, but again, it will be very painful, a lot of operation, a lot of verification. For example, if you make a test with a product with helium inside, you test it, it's tight, okay? But you will have to perform a plausibility test in order to prove that you have still helium inside your container to confirm the test. Because as you know, if you put helium inside the container, if for any reason you have a gross leak, the helium can escape very easily through a gross leak. And when you test the product, perhaps you will have no more helium inside. So this is a thing you have to consider, and it makes the helium test quite difficult to set up in production. But it's possible. Some companies are using helium test to perform IPC test. That's for me. Except if you need to reach a very low, again, reject level, which is not most of the time the case, it's not justified. It's too complex, but it's possible.
One more question out of the audience regarding the OES technology. Do you apply vacuum or overpressure for optical emission method?
We apply vacuum. We apply vacuum for all our technology. We apply vacuum around the container, and we measure the gas escaping from the container through the defect.
Exactly. So, any more questions out of the audience? Otherwise, okay, nothing is coming. Yes, Philippe, do you have any last words or something you want to maybe to give on the way?
On the way, no. First, I would like to thank everyone to participate to this webinar. I just want to perhaps to show a slide regarding the result of the last poll. 17% of people answer get higher throughput, and we can imagine a typical requirement, typical customer requirement, and what can be proposed. So let's consider this requirement. Test of glass vials, glass ampoules, 20 ml, with liquid and or lyophilized drug inside. Detection limit 1 micron, sharp edge surface. Throughput 10 part per minute. Test unitary, unloading and loading of the container, manual or automatic. What we could imagine, and this is a real customer requirement, is to address this application with almost no limitation regarding the type of drug, liquid or lyophilized, with 2 IMI equipment and 1 operator. So the operator will load 1 equipment when the other one will be tested, and after he will unload the second one when the other one will be tested. So it's quite efficient to get a higher throughput. And as I told you during the presentation, in this case, we could imagine to replace the operator, because again, the operator has no real added value except to load and unload the parts. So for example, to use a pick and place robots. And we could also imagine not to test the part one by one, because this technology is able to test a complete batch of products, easy for 1 micron detection limit. And for example, you can decide, if you want to increase the throughput, to test a batch of 5 or 10 products simultaneously. And in this case, we can easily increase the throughput up to 40, 60 parts per minute with 2 equipment. So this is something quite interesting, because as you can see, a pick and place robot is not something very expensive. So the cost of automation can make sense in regard to the cost of an operator. And this is something we can propose with this technology, the test per batch and a quite high throughput, because again, depending on the reject set point, we can test 5, 10. This is just an example, but for 1 micron, probably we can test 50 at the same time. Of course, the result will be a global result. That means if it's tight, the 50 samples are tight. If it is leaky, 1 or several samples are leaky, but you don't know which are the leaky samples, and you have to retest with smaller batch or 1 by 1 to identify the leaky part. but it can really make sense to dimension, to size the batch in respect to the quality of your production. If you have one part on 1 billion, which is a leaky part, you can test per batch, and this could be a great benefit if the throughput is a concern for you. This is my last comment. If there is a new question, I'm really happy to try to answer to this question. Again, thank you for your attention and to participate to this webinar.
Unfortunately, there's no more question, so everything seems to be clear. But for sure, afterwards, if you had time to think about the webinar, for sure you can feel free to just reach out to us, and we will be happy to help and answer all your questions, which might come later.
Yeah.
So then also from my side, thank you, Philippe, for the very good presentation, and thanks to all the audience for the time this evening or morning, depending on where you are, and a nice rest of the day. Thanks to all.
Thank you. Bye-bye, everyone. Have a nice day.